Now we're starting with chapter 6. This is an image of Salt Creek Falls in Oregon, and it's about as fast as water can flow in a stream. It's on the Willamette Pass of Oregon, just outside of Eugene. So we'll start with a global distribution of rivers and streams, and the intermittent rivers are given in B, and the perennial rivers are given in C. We can see that some areas that are drier, such as the Southwest United States and much of Australia, have a really high numbers of intermittent streams. Areas that are wetter, like the Arctic, for example, and we discussed why it's wetter. It's not wetter because there's more precipitation. It's wetter because of what?
Less evaporation.
Right, less evaporation and cooler temperatures. Good. So those have less temporary streams or intermittent streams. And then some areas that are just so dry, you know, that just have no permanent streams, like the Sahara does have some intermittent flow. So that's a good indicator, and we'll get a little bit more into that of high evaporation relative to precipitation. That is actual versus potential evapotranspiration. We're going to talk about how to characterize streams, stream flow and geology, and movement of materials by rivers and streams. When you look at a stream, there's different ways to characterize it. You can characterize it by the watershed or catchment size, by order, by discharge, flow regime, and vegetation, and we'll discuss all of these. The top one, watershed or catchment, is differential terminology. Catchment is what British English speakers use to determine watershed. Both mean this in American English, and watershed and catchment in English mean the same thing, and that is every point above the point you are at in the stream that drains into that, right? So the entire area above one point that drains into that is what we call the watershed. In English, the watershed is the ridge between catchments, which actually makes more sense because it is shedding water into one or the other. So what's the one that divides, the watershed in English terms that separates where water flows to the Pacific or the Atlantic Ocean in the United States?
Continental divide.
Great, the continental divide, right? So we don't have a real name for that other than the continental divide, right? But in English, that would be the continental watershed or something like that. Okay, so we'll call it watershed from now on. But if you get into literature, maybe one of your papers you're reviewing talks about catchments, and now you know what they're talking about. So this was on your quiz, Strahler stream ordering, and it's just one way to talk about what the sizes of streams are to classify them. And the smallest streams are first order streams, and if two first orders come together, they make a second order stream. However, you have to have the same order coming together to increase the order. So in this case, on where my cursor is, the second order has a first order flowing into it. Yet it doesn't increase order because that's a first order, that's a second order. And it goes by another first order again, right? All of a sudden here it hits a second order coming in this way, and it becomes a third order stream. And it stays that way until 2/3 come together and it makes a fourth. Pardon?
Is determining the order a function of one thing? Like, are the ones always on the outside, or is it about how thin they are and how, yeah.
Okay, so the first place there's active flow in the channel, right? And this is a little bit fuzzy because some people say you have to have permanent flow for the first order stream to even occur. In drier areas, oftentimes people, like on Kanza, where we have intermittent streams, we look more to where there's been geomorphological activity, and you can see there's a channel there that is not necessarily always flowing. But in any case, you go as far up to what you think is the smallest stream in a watershed, and that is your first order stream. Okay, then you work downstream from there. And you've got to have them all, because you need to know where they all are. And
Okay, and just because of physics, the outer ones are going to be your smaller ones.
the ones highest in the watershed. So this could be, I mean, this could be
Yes, okay.
angle, right? Yes, that's correct. In addition to order, we can talk about the arrangement of streams. So we can think about this, we oftentimes think about this as being a typical arrangement, but you may have some geology like karst geology that kind of makes cracks or something where things flow actually sort of rectangularly. When you get into drier areas, like in the desert where there's a lot of unconsolidated sediment and intermittent flow, a lot of times there's these really long parallel drainages. And if you drive through the western U.S. and look up on the hillsides and you see a steep hillside that's sort of sandy or soily without not much vegetation, oftentimes you'll see these really long rills or drainages. And then this dendritic pattern can be generated by simple mathematical properties. And we'll get back to this at the very end, but this is just an example of a computer simulation that made a river system. And you look at it and think, yeah, that looks kind of like a river system. That would be natural. Another quiz question we had. There are more small than large streams. Okay, so we look at stream order. So first order streams tend to be pretty short. They tend to be less than 1/10 of a kilometer long. In this region, this is just one area that they're all counted up. And as you get to the larger streams, the 7th order, they tend to go pretty far. It takes a long time to get far enough that for a 6th order to get far enough that another 6th order came in, even longer for a 7th order before another 7th. So the total length on average of these higher order streams is substantially larger than each of the low order streams. However, the numbers are vastly different, right? So in this particular large watershed, there's more than 10 to the 6th first order streams, and just maybe 100, right? So that's 1, 2, 3, 4 orders of magnitude, 1,000 times more of the smallest stream than the largest stream. For that reason, if you sum up the length, the length times the number, right, you get the total length. And for that reason, there tends to be more shorter streams, length of shorter streams than longer streams in most watersheds. This is not always true. You can, for example, if you have a terminal basin where the larger river then is drying out as it goes into the desert and then just goes away, it may not be. It may be even longer. So there's different reasons why it may or may not be true. But in general, if you go across the whole world and look at it, most of the length of streams in most watershed is in smaller streams. This has practical applications because it is the interface then between the land, the dominant interface between the land and the freshwater systems that are downstream, right? So basically you've got more riparian zone then, a longer amount of riparian zone in the first and second order streams than you do in essentially all these streams down here. So it's really important for water quality, and a bunch of other factors and ways that things that influence the ecosystems of streams and how they operate. Has everyone got that? Okay, good. So, I mean, one of the things that we also look at is streams when we walk up to a stream is you go, well, how much water is flowing down that thing? You know, is it deep or fast enough that I can walk across it, or do I need a boat to get across it? Those kinds of things. Remember, when we talk about streams, we talk about what is the flow. And that's a nebulous term because it can mean discharge or velocity. So discharge is the volume per unit time. It could be liters per second, cubic meters per second. USGS uses cubic feet per second. And velocity is how fast it is meters per second, right? It's the average velocity. So in the field, when we were trying to estimate discharge, we relate the two. We get average velocity across the entire area of the channel, right? So that's meters per second. And if we know what the square meters of the stream channel is and the average velocity, then we can get the cubic meters per second. So velocity times area, meters per second times square meters equals cubic meters per second equals discharge. And we can think about how this changes over time with hydrographs. And it's a way to make a graph. And here's some examples of some contrasting hydrographs. And A and B are a long term, and then a year, so multiple years, and then just a year on the left and the right of the Niobrara River, and that is a river north of us in the sand hills of Nebraska. It is mostly a spring-fed, groundwater-fed system because the rain falls on the sand and it just works its way down to groundwater. So if you get a big pulse of rain, a big rainstorm, it's spread out over everything, getting into the groundwater, and can bring up the discharge somewhat.
Are you right now talking about the top right one or the
top two, the top right and left. So this on the left goes from before 1960 to after 1980, and on the right, B is just 1 year of that stretched out.
Okay, so that's why it's less stark changes. Okay.
Right, yeah. So this happens to be a really constant year, right? It's not changing, there's a log scale still, right? And it's not changing that much, but maybe fivefold or something like that over the year, with more flow in the spring and maybe when snow melt occurred here. In contrast, we have Kings Creek, which is just upstream from where we took a field trip. And I've had to add onto the discharge 0.001 to get it on a log scale. So anytime it's down at this point 10 to the minus third, right, that's actually zero flow, because you can't plot a zero on a log scale. So that's why there's these parts in C and D that are down here just flat, right? Those are zero. That's when it's dry. So this is a intermittent stream, and in this case it's flowing for more than half the year. And this 1 year in 1990, it flowed for more than half the year. Had a really big flood in 93 here. We had a number of years where it dried a little bit, but mostly flowed. Usually the main parts of the flow are in the springtime when we get the heavy rains, but in this case there was also a thunderstorm that made one quick flood and then went away. Okay, so this contrast between constant flow and not so constant flow. And then the extreme here is this Slaty River, and the Slaty River is on, the Slaty River in E is on the west coast of the South Island of New Zealand. And that is a place where there's large mountains and marine weather coming in. And so you get repeated large storms. This is a river, we can see this is just like less than a year's worth of data, right? But we get flood. It floods like every week in this river. You can imagine that all of these things have effects on the organisms. And this particular stable flow, organisms is pretty benign for most organisms. They don't have to get away from it. This intermittent flow, an organism would have to get out of here or die, right? This is such extreme disturbance that actually, if you go collect invertebrates in this river, in the Slaty River, you can't get any. No fish can stay in there really and survive. The invertebrates can't survive. They can't even get a generation off before they get blown out by the floods. So those are some sort of extremes as far as discharge goes. Then we can talk also about the large rivers and how they flow, So this is the Missouri River from 2020 to 2000, going all the way back to 1930. And we have 2 years, one 1930 here and one 1980. We can see in general in A that the variation from year to year is substantially higher in prior times than it is here. And you can also see that there is an annual variation that is greater. We get a nice high spring flow, and it goes way back down during the winter time, and then comes back up, right? And that happens in the 1930s. In contrast, it's low, and then it pops up, and it stays pretty much the same, maybe a couple of blips, and then it pops back down again at a very specific time. What do you think explains this change in flow regime in this particular river? What do you think has changed basically since, the 60s and before relative to over here, where we get much more variation here and much more variation within a year here in the 30s and 40s than we do now since the 60s, 70s, 80s, 90s? Anybody think of potential major changes on a river? I had somebody say farm uppage, pollution, probably not. And I think Maxwell Burden wins the prize. Reservoirs, right? They've controlled the flow upstream. And there's a number of really, really large reservoirs upstream. In addition, there's another, so part of this is for flood control, but another part of this has to do with transportation. And what do you think this is? What else is the Missouri River used for? What is the Missouri River used for with regard to transportation?
Is it the river that is basically, there you go. Somebody in the chat said cargo.
Cargo on what?
Steamboats.
Not steamboats anymore. Maybe in the 30s it was steamboats. What are they now? Barges, right? Yeah. So there's barge traffic, and the Army Corps of Engineers is supposed to manage the reservoirs, 1, to keep flooding from occurring, and 2, to keep water high enough so the barges can move their way up the Missouri River. It's become less and less important as more and more of our cargo is carried by trucks on highways, but it's still something that goes on. So they keep the flow high. They have a mandate to keep the flow up to a certain level from sometime in the spring to sometime in the winter and in the late autumn. And then when there's not going to be any more barges, they're like, okay, we're shutting it down, and boom, down it goes. Okay, so we've got this major influence on the hydrology. Most large rivers in much of the world now, if there's population near them, are regulated by reservoirs, and it changes their flow, their hydrographs.
So the right half of the top hydrograph is due to regulation. They keep it within a margin.
Yeah, look at this variation here on the left half of A. See how much bigger it is? And this is the log scale here, right? Relative to here, things are calming down. Now, when we get into the 93 floods and the more recent floods in the last few years, at some point the reservoirs can't handle it anymore. So you'll get some of these really big events, like here's the 95, here's a flood in 96, I believe it is. And here's another flood back here. Everything just, all control went away at that point. There was just so much water. And so at some point you can't control it. And then you get into things like levees breaking and some major damage. It's a good question, though. Okay. So then we can think about how we've modified flows and how typical flow. So this is a typical hydrograph of one event. And we have rainfall here, so we get this rainstorm that leads to some amount of rain over a certain number of hours. And then there's a time lag after that, where we have a flow, and we have what we call the rising limb. We have the peak discharge. We have the falling limb. And then the flow after that's gone is called the base flow. And that could be mostly fed by groundwater as opposed to overland runoff. If we urbanize a stream, if this is the same stream and we have the same event, then the peak comes quicker, the rising limb is faster, and the falling limb is faster. So what's the reason for this? If we urbanize a stream, that we get this flashier flow. Limb, L-I-M-B, Emma.
Oh, maybe like big fat drain systems that can make it leave really fast.
Channelization.
Yeah, channelization, drains. And there's something else that's important here.
Culverts.
Yeah, Max got it. Impermeable surfaces. Man, my nose itches. I think I got allergies. Yeah, impermeable surfaces. So we've got a situation right here that is doing that. That on campus, they've built more and more buildings. They've put more and more concrete in. And downstream, they changed the zoning so they can put apartment buildings as you work your way east of campus. Apartment buildings are only required to have 14% impermeable surfaces. The houses that were there before were usually more than 40% impermeable surfaces. So rain, when it falls on the apartment buildings, shoots into the storm sewer systems and starts overwhelming them, and more is coming in from above. So we're getting more and more flooding in town because of impermeable surfaces and not an increase in the amount of drainage. Otherwise, the water would fall and it'd work its way slowly through the groundwater, and we'd have more of this kind of hydrograph, right? It'll come out eventually, but it takes a lot longer for it to do it. So the severity of the floods is not as high. And here's another watershed with some real data. And we see from 1931 to 1959, before urbanization, the recurrence interval, the frequency that each event occurs in years. And so in this case, a 30-year flood, one you'd expect one in every 30 years in this watershed, was at 400 cubic meters per second. However, after this watershed was urbanized, all of these went up. So in this case, a 30-year flood is somewhat more like almost twice that amount of discharge, right? So you have to change the expectation of what a flood is. Floods become more intense and more difficult to deal with. We have the formation of riffles and pools in streams. So we're getting into the geomorphology part. And the first one, going downstream, water flows downhill, and pools are deeper and slower. Riffles are shallower and faster. A riffle, you can generally see the surface, the effect of the bottom on the surface of the water, whereas a pool, you can't see that. This shows the fastest part of the stream, the thalweg, moving down the stream. You can see it's moving across the stream. As it moves to the outside of the stream, it is moving faster on the outside than the inside. It's just the centripetal force, right? And this bank is pushing it, so it's moving faster here than here. This cross section shows that. So if you put A here and A prime here and look at the cross section down through this, you see the very fastest flow is near the edge, is near the outside edge. It's slowed somewhat as we get near the bottom because of the friction of the bottom. And the slowest flow is on the inside of the bend. In addition, as it flows there, it's flowing faster on the top than the bottom, right? And particularly on the outside. So flow is cutting down on this outside. It's cutting down towards A, moving across the bottom and going up here. And then, so the flow's slower here, and it's cutting sediment on the outside, coming up here and dropping the sediment. And this leads to a point bar. So there's erosion here and deposition on the inside. The point bar then is building this way, and this is cutting out this way at the same time. If you get right at that crossover point where the riffle is crossing over between one side and the other, then the water velocity contour is the highest in the center. And it gets slower and slower as you get towards the bottom.
Why is that water, why that first curve, the Thawwig, why doesn't, upon hitting that far wall, why doesn't it slow down? Like, wouldn't hitting the wall and having to change direction take from its...
It slows it down, but remember we've got a gradient here, right? So gravity just keeps moving it along. So it was at whatever average velocity came in above, but you're dropping down here, so it's going to move fast again, and slow down, and move fast again, and slow down. But yes, it will slow it down. It'll get more friction there. Good question.
But it's still the fastest moving water, even if it's slowed down?
It's slowed down, but everything's slowing down, right? So it's faster than the rest of the water.
The rest of it. Okay, okay, okay.
And if we look at that, the flow again from left to right, the porous bedrock is not going to allow any flow through it. But these gravel bars that form where the riffles are, there's actually going to be a modest amount of flow through these. And so this will have an ecological effect as well. This zone in here where the groundwater is interacting with the surface water is called the hyporeic zone. Hyporeic, hyporeic. This is a distinct habitat in rivers and streams. So this is forming meanders, and meanders get bigger and bigger as you get larger and larger streams. So if you have a larger surface drainage area, your meander lengths can be 10 to the 100 kilometers or more. So the Mississippi River, the Ganges, the Amazon, some of the world's largest rivers have very, very large meanders. And the meander is from the cutting out, right? And coming back and cutting out the other direction. So it's moving through the watershed over time. And eventually, when you have a meander, so here's a floodplain. This is where the flood will go throughout the river. There's a sinuous channel here. And the oxbow, right, at some point, the flow was out there, pardon me. The flow came out here, right? But at some point, the flood came and cut it off, and it left behind an oxbow lake. So this is the idea of meander, right? And this one, it hasn't cut it off yet. So the meander is going way out here. Over time, this means that rivers move back and forth across their floodplain. So the bottom shows this, where you can see how there's an oxbow that just cut off, but they're both flowing. Here, there's a series of old oxbows that were left behind as this meander moved further and further out. Maybe you'll have a permanent lake or something. There can be marshes in here. This leads natural rivers and streams that are not channelized, that don't have levees pushed up against all this, to form wetlands, to form complex habitat. You can have sandbars, you can have more permanent riparian vegetation, you can have wetlands. As you channelize the stream and stop the flow variability, you decrease this habitat complexity.